Okay, one person knows, good. So that means the rest of you will maybe learn something today. Otherwise, you will recap something, who knows? And I want to ask you, do you know why PageRank is called PageRank? Any?
Ranks pages?
Yeah, ranks pages. Any other clue why?
I think, well, according to my reading, because I used PageRank in my research in the recent 2 years for system dynamic simulation to quantify the complex adaptive network. So I used PageRank with a little bit tuning of the algorithm. So Larry Page, the founder of the Google, I think during his PhD, came up with the algorithm to quantify the Google page. So I'm not sure whether it's his last name or just the page.
Yes, you're very right. So I'm glad you know. So if my pointer will not fail me, and I don't know why it's failing me, I'll then try to, let me go to the next page. Okay. So
Yes.
This is the page, Larry Page. Maybe now some of you know, and we'll talk about his rank today. So this Mr. here, he did his PhD, or not, he started his PhD at Stanford on analyzing web links. In the process, figure out how to rank things well. Didn't finish his PhD because he had some trouble, of starting his business, and his business was called Google. So, and the rest is history. So, to some extent, PageRank is basically this algorithm is the start of this multi-billion, multi-billion-dollar business and the foundation of Google. And we'll talk about it today. Now, the formula, I didn't find it on the curtain. Maybe I was not very, precise. Maybe nobody put it there. But if we put there, we'll probably put something like this. And you might be now a bit confused. What is there? Don't worry. By the end of the talk, hopefully all of us will know what each of the components mean. You might also see the other type of formulas, which are also PageRank. So there are many different interpretations. This is a bit maybe more linear algebra view, and the more general one. This is more of a classical one, but we'll talk about them later today. All right, so a bit of history. How does that start? So I see that all of you are very young here, so I don't know, do you remember such a web page?
No.
Oh, some of you? So back in 90-something-ish, when the web started appearing, when the more and more web pages popped up, people needed to find stuff, right? And we didn't have Google, right? This is by definition here. So it wasn't easy to find. So smart guys actually founded Yahoo on the basis that they employed many people to manually find the pages, put in the directories, and there was the science, and they put some science pages, and then there are some education universities. Probably KTH would end up there, and then Stanford and MIT. So basically, this was a web curated directories. Okay, so it worked for a while, but since the web was exploding, it you couldn't keep up manually with everything. So this started being, how to say, very limited, and you couldn't find new stuff. And then other things appeared, like Alta Vista. Have you heard of Alta Vista? Okay, so that was already a bit more smart search engine. So that was, we could call it the first one, like a first generation, just manually created. This was the second generation. This was based now on the state of the art back then, information retrieval. And what they would do would be the following. So they would crawl the web, with all the pages they could find, had a very state-of-the-art indexing algorithm that could very quickly respond to any query. You say whatever the Michael Jordan, and they would find very quickly out of these millions of web pages, set of pages with Michael Jordan, and they could send it back to you. Now, the problem was that there were quite a few pages with Michael Jordan on that query, so you need to rank it. And they had a bit of a problem with that. So they tried to attempt to rank based on how often this Michael Jordan would end up appear in the page, or maybe whether it's appearing in the title on a header on a page or something like that. And it was okay, but still you would search and some random things happen. But the worst sort of thing came on a curse on the second generation engines, were that there were very, how should I say, bad people who were using term spam in order to increase their own web pages. So they would think, aha, people search a lot for Michael Jordan, or maybe movies or whatever else. So they take my web page that I sell some pencils, put at the end of my, I know it's about pencils, but then at the end I would put Michael Jordan like 1,000 times, and then Star Wars, and 1,000 times. I put it on the white background with the white color. So if you come to my webpage, you wouldn't notice anything. But all the Alta Vista information retrieval engines would index it, and whoever searches for anything, your pencil webpage would pop up. So basically, they were spamming with terms. Back then, you couldn't have a Google Ads, so that's how you would make your rank higher up. So basically, the thing was that the search was not existent back then. And that's how, the sort of story of Larry Page maybe starts, where, people are having this explosion of of World Wide Web, and then you cannot find anything. It's very frustrating. So what Larry Page thought about is that the web is not only about the content, because that's what it was up to now. People read what is there and tried to make sense of it. But there's also a very important signal that there are links, hyperlinks of the between the web pages, and they were completely underused or not used. I think Alta Vista would put the web pages, these links in their sort of search results, but they wouldn't do anything about that. So what, and it's even Tim Berners-Lee, who is the inventor of the World Wide Web, already envisioned that the hyperlink should be the sort of the basis of how we consume the web. You should surf from one page to another, search for the information. So this was, in a sense, not used at all in any way. And also back then, other network science fields were gaining popularity. If for example, Small World Phenomena was having quite a bit of research there. Watson Strogatz, had their model in around 2000s there. All these 6 degrees of separation were, coming back, people were analyzing. So people thought that looking at not at the content, but at the topology, you could extract more or other useful information that could complement the, say, information retrieval engines. And Larry Page thought that this is similar to academic papers and academic citation networks, where sometimes if you didn't read the paper even, but if you know how many citations it has, you could say, maybe that's an important paper. It has, 150 citations. Not as important maybe as this with 3 citations. So in a sense, this was the clue that for ranking web pages, we should use the topology, right? And basically the insight was that believe not you say about yourself in your web page, but what people tell about you by linking, because it's very easy to fake your own web page, just writing this, 1,000 times Star Wars, and it's very hard to convince others to point into you, right? So that's so if you count the links, maybe something good can happen. All right. So then, the idea of Larry Page, I don't know if it is his idea or his supervisor, that's already back in history, but to exploit the structure of the web for ranking the pages. Now, it's easy to say this, okay, let's take those who have most links, and that would be it. That wouldn't be exactly PageRank. You just count the degree of every page and then sort it by that. Maybe it wouldn't be bad, but it's not, maybe not enough. So what we could say that, first of all, the page is more important, it has more incoming links. So that degree. So let's now complicate a bit. Let's or maybe before saying complicate, was the problem. The problem is that not all links are, how to say, are born equal. Some links are better than others. If a Nobel Prize winner cites you, maybe your paper is better than if your a colleague next door cites you, right? So then maybe we should count a bit different these incoming links. So we should weigh them somehow. Because if you look at any network, especially World Wide Web, some nodes have lots of incoming links, others not. So in a sense, wikipedia.org probably would be, quite a authority to point into you, and then some joeschmo.com, if it points into you, maybe it shouldn't make any big difference, right? So what we want to say that besides that we should count in links, we should also weigh them by importance. So the links from important pages should count more. But now you see this is a bit of a recursive argument or recursive reasoning. So now we'll have to take care of that, and that's in effect what will PageRank be about. So okay, let's be a bit more precise. So let's say we take node J or a website J with its rank. So basically this page J importance will be sort of as a voting rights towards its our degree of the hyperlinks that it points to. So if it points, now I have an issue with maybe you see it anyway. So there are 3 nodes that this J points into. So what we will say that J will give equally its rank to each of the neighbors. So if we had some RJ rank, equally divided by third, pushes to the neighbors. And similarly, J's rank will be determined by the incoming links from its own in-neighbors. Right? So if this I now had 3 outgoing links, because we only talk about how we send out the outgoing links, so then it would give to J R its own rank divided by 3, while this one would give only a fourth because it has 4 outgoing links. So it's in a sense easy peasy. We say that a rank of a J would be just a sum of all the ranks that J is pointed into, but weighted by the degree of each of the nodes. Meaning that if you have a lot of neighbors, then you will give a little bit of your rank. If you have only one neighbor, you give all your rank. So this is sort of this first iteration of calculating the rank. Now, we could maybe make it a bit more beautiful if we now move it to the bit of linear algebra perspective with matrices, right? So we can do the same thing. And now we'll operate on this graph. And I don't know if you see this graph now has some directionality. We have 5 nodes. So what we're going to do, we're going to first define so-called stochastic adjacency matrix M, or sometimes called transition matrix. And this matrix will have the following. If a node, let's say 5, points to some neighbors, so say it points to 4 neighbors, then at MJI, we will put 1 over the degree of that node. So for example, here, we would show that node 5 is going to distribute to its neighbors, to the first neighbor, third, right here, to the second neighbor, third, and to the fourth neighbor, third, right? So basically, and the matrix, I didn't explain, but I hope you understand, this is the square matrix with the number of basically of number of nodes. We have 6, so it's 6 times 6, and every column and every row represents the relative node there. And now, if you look at the horizontal lines, we could see how much, say, node 2 is going to collect from its neighbors. So now, if you look at node 2, so it has 1, 2, 3 incoming links. So from 5, it's going to get a third, that we know that's what 5 is giving it. But if we see at 1, it will give a half of its rank because it has 2 links here, while from 3, it will get everything. 3 has only 1 link pointing, and will be nothing from the others. Okay. So now we prepare this matrix, and then we can also prepare the, say, initial rank vector. And we say, let it be stochastic. So we know it should be sum up to 1. So then let's start it with a 1/6 as a importance in the beginning. And now if we want to execute this our formula from the previous slide, we just need to multiply this matrix with this vector, and we get now updated ranks, right? Because it's, I mean, what we do is basically we do dot product of the rows and the columns. So say for this second one, it would simply get this new rank 0306 because it takes half of the first rank, you know, full third rank and third of the fifth rank, and the rest would ignore. And that's how you do basically for it. So it's pretty easy, right? So now we have a rank that if we didn't need to do it recursively, you could now maybe, I don't know, rank something. That would be maybe not a perfect rank, but you know, something. You could do the same with any other stochastic vector. Say you put everything 0, but only 1 on 5. So say nobody is important, only this has importance. And then after first iteration, you could see how the ranks spill out. So basically, it would spill out a third to 1 second and fourth, and the rest will have 0. Right? Okay. So here, and that we will write it like this, where we multiply the transition matrix M times the old vector, we get a new vector. Okay. Now, we could do the second time the same thing. So we could, whatever, you know, we have from the, in the sort of second time step, if you want, we can now multiply again and get something new. So in effect, it's the same as you take the initial vector and let it be multiplied by the m square. Because basically you square the m and then multiply with the initial vector, and then you got this second sum. Or you can be in a more general terms, you cannot see now again, but you can take m to the power of t, multiplied by the initial vector, and you get the whatever the vector at time t. And maybe, you know, after t times, you already have a good rank. Who knows? By the way, you can always stop me and discuss. I would be very glad to take the questions. I don't know why it fell down. It had to be upper script here. So this is just a vector. So, okay, so what happens now if we take it like step by step, if we started now, say, with this vector, and we multiply step by step with matrix M, you could see that this changes to rank this, and then we can go on, and we can go on many times, and suddenly, say in the time 55, we see that the ranks stop changing. Okay, so basically we got some rank that when we multiplied with this matrix, it spitted out the same rank. So we say we converged. And there we could already say, maybe that's not a bad ranking sort of a situation. And maybe we can use it as a rank, just order the nodes by importance. So we can even see, you know, that, for example, the first node seems to be has the highest rank, and it looks like the right thing because it has many incoming links from quite important nodes. While what is this fourth node is quite unimportant, and probably it is because it's in the periphery. And actually, you could have started with any stochastic vector, and it would be something different here, but at the end, it will always be the same. It would converge. It is a bit of a caveat. It converges for this graph. We will later see where it can have some pitfalls.
Okay, so is it because that the m has an eigenvalue 1 and its prefix norm is smaller than or equal to 1? So
but not all m's could have it. So you have to construct it very carefully in order to have it. So basically, only some of the graphs, when you construct M, would have this property.
Okay.
And some other graphs that we'll see later would make us problems. And that's what Larry Page had to solve, because otherwise it would just just do this power iteration, or as you now see, this is basically an eigenvector of this matrix with the eigenvalue 1. You just take it and then rank your stuff. So we'll see a bit complications will come later. But for now, that's what we have. And actually, you can do it for weighted graph as well. So you can prepare if you have some weights. So basically, the links are different in different capacities or fatness. You could represent it the same on the matrix. So say number 5 has still 3 neighbors, so the same directionality, but the neighbor to the one from 5 to 1 is fatter than the rest. So you would represent it in the same way here. And then you could do the same thing. The matrix M is still stochastic, meaning that the columns sum up to 1. And if you do this exercise, we would converge as well. Okay. And we can even see why I cannot change. Okay. We can even see how it converges. So now it converges, but to different ranks. So naturally, this graph is different than this, although very similar. And the ranks would be a bit different. So if you look at, say, node 2, so in this graph, it was the second best. But now in this graph, it's not the second best anymore because it's maybe the fourth best. Because although it had some incoming links, but this is so thin that they almost didn't count. And then these guys probably took more of the rank. Okay, so just to say that it works on both weighted and unweighted cases. And as we already discussed, you can interpret it with the eigenvectors, meaning that the rank of your, say, web pages can be extracted by first constructing this transition matrix M and then finding the dominant eigenvector. And in this stochastic transition matrix is basically the eigenvalue 1 eigenvector. Okay. And that's very generically what PageRank about, although there are many things to solve later, but that's the basic principle. Another interpretation is that you can think of it as the random walk on graphs. So and random walk is basically if we take a graph and start randomly walking around, and then we count every visit for every node. And after many, many walks, we see how often random walk visited each node. So our eigenvector would be nothing else as a sort of time, would represent the time spent of a random walker at each node, or a stationary distribution of a random walker, right? So basically, it is modeled with the same thing. And then if we start with as we saw before, with the initial vector where there is everything 0 except 1, where we start the random walk, we do the same thing. And basically, what we end up with is it's very slow animations on my laptop without connection is much faster. So basically, just says, as we discussed, fraction of time that random walker spends at each node. And basically, in this node 1, it will be maybe 31% of the time is there. Now, the thing is that now if we look at the questions, and you might have asked me whether we can always converge, whether we can converge to the same thing all the time. The answer is that random walk always converges to unique station distribution if we don't have issues with connectivity. And now we can discuss what kind of issues we can have. So now tell me, I give you another graph. This is the graph. And this is the, say, random walk that starts, say, with the node 3. We go, 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 go. We ended up here. Any issue here that you see? Yeah, so we have zeros here. For some reason, node 2 and 3 got zero rank. Although it's, this is 2, this is 3, they are looks like a valid nodes. Why anyone sees what's the problem?
Circle, green.
rank sink?
Yeah, so there is a sink. So what we sometimes call it spider trap. So if you could see, there is some component here that basically can go around, can reach anyone. But from 2 and 3, there is only one-way streets. Okay, so all the ranks that were there eventually will be sucked into the spider trap. And that's why you could see that at some point, maybe the 2 and 3 had some ranks, but eventually they leaked out to this area. And now it's mathematically not a problem. Random walks converge. It's a unique distribution, but it's not cool because we have some nodes that we cannot process. So we call it a spider trap, and then we'll discuss some solutions. Maybe we have them to make sure that there is a link back. So in a sense, we want to make the graph strongly connected, and strongly connected graph means that any node can reach any other node in the graph. And in this case, these nodes cannot reach 2 and 3. So this is a problem.
May I ask a question?
Yes.
Just asking, because I use this method in my paper, so I'm not sure whether it's good or bad, but wouldn't tuning the damping factor help a little bit of solving such? Damping factors are very vague way of interfering on how the algorithm works, which is still vague for me also. That's why I'm asking the question to know.
I think we will come to that, your question. So when we'll talk about teleportation. But if you notice, now at some point you will hear word teleportation, which will be something unique to this method, but we haven't gone here. So far, we are just identifying the problems. Problems with a simple random walk on the not very nice graphs, if you can say a graph with the spider trap not nice. So let's first identify the problems and then see how we can solve them. Other problem. So a graph could also be disconnected graph, right? So now if we start with the random walker from the node 1, at some point we end up with such a distribution. And not surprisingly, the distribution is only about nodes 1, 2, 5, and 6, because there was no way it could reach there. And if we had started, say, at node 4, in that component, we would have ended up with some values for 4, 3, and 7, but nothing for the 1, 2, 6, and 5. Right. So again, it converges, but now the distributions are not unique. And we get zeros where we don't. So again, it's not very cool. So that's the problem with the disconnected graphs. Right. So again, and then if we want to solve it, maybe we need to connect them somehow. More problems. Can you see some issues here? That's very bad, no? We started random walk at 3, and then walked, and now something became 0. Any clue why? Okay, I'll help you. Look at this node. It has no out degrees. So to some extent, everything it absorbs, it doesn't spit out. Because up to now, if you noticed, all the columns were still summing up to 1. So we never lost the volume, say, of our rank. We started with some rank, we just do the redistribution at every node, but still the whole volume is preserved. Stochasticity is preserved because everyone has some out degrees. Now, in this case, this guy doesn't have any out degrees. So when it takes in the rank, it doesn't get it back to the system. And then it basically leaks. And that means your columns become summing up not to 1. And at some point, everything leaks. And that's why, because our matrix that we form is not stochastic, it's substochastic, because the number 4 column is 0s, because there is nothing here. So that's a bit of a nasty one. And then again, the question is, what can we do about that? So what we can do is maybe, I don't know, get rid of these nodes, just prune them. I mean, we don't need them. Or another thing where let's put a self loop, and that's already to make the matrix stochastic. Then we at least don't we don't lose the rank. It doesn't spill out. So there could be some fixes there, and we'll see later what we do. Okay, the last issue. Can you see what's wrong here? It doesn't converge, it oscillates. So you see, it has something at 1 in the 4th, and then it has something in the 2nd and the 5th, and then something in the 1st and 3rd, and again, something on 4th. And it goes forever and ever. And the reason why, because the graph is periodic. It has periodic behavior because it has cycles that have the least common denominator or the greatest common divisor or more than 1. In this case, it's 3. Meaning that if you start, say, at 4, here you can now go only either to 5 or to 2. So at the first sort of step, it's always here. At the second step, it has to be either here or there. At the third step, it has to be either here or there. And then again, we go here. So there is no way to sort of break it out, and always cycles. So this is periodic behavior, and it's also not cool because it doesn't converge, it oscillates, and you cannot make use of the rank anywhere, right? So this is maybe more of a theoretical one, and if we, because it's not that often to have in a big graph a periodic behavior, because like if you only put a one link back here, you already break the periodicity and you could converge. This is now on this new graph with this link. So basically, this is more of a theoretical problem, not a real problem, but still just that to illustrate. So there are this number of problems where we cannot achieve unique station distribution from any distribution in certain graphs. So what we can say that the random walk always converges to unique station distribution only if the graph is strongly connected, meaning that you can reach any node from any other node. And there is this another caveat, should be aperiodic. And it also, if you work with Markov chains, is basically the irreducible aperiodic Markov chains. And there's an ergodic theorem that also says the same thing, that any stationary distribution will sort of be converge to a unique station distribution. Or any initial distribution will converge to the station distribution. So now if we want to apply it for the World Wide Web, how does World Wide Web look like, the web, right? And probably you could expect that it's not so pretty. So there was a work back in already 2000s where they analyzed like some millions of nodes in the web, and they ended up with this so-called bow tie structure of the web. So you see there is the big bubble with few bow ties and some tendrils around. And what they found that there is strongly connected component. Yes, it's a pretty significant 56 million nodes. So here you can reach anyone from anyone. That's fine. The problem is that there are these bow ties, 44 million nodes of the in component, where it's sort of it goes in like pages that sort of flow into this component, and nobody can reach them, right? So they are sort of one-way street. And there's an out component, similar just the other way around, where basically it consists, it's also 44 million nodes. And by the way, this is just an accident, that it's not that, it don't have to be the same numbers, but just so happen to be similar. That again, they probably have many spider traps or dead ends that also go only one direction. And then there are these weird things like tendrils, which go from in component out or from the out component in. There are some tubes, and they're also significant, also around 44 million. I have no idea why there are so similar numbers there, but they don't have to be. There's nothing fundamental there. So what it means is that our graph, if you just do this initial PageRank formula, you would not converge. Most likely you would leak out here and everything will be 0. So we had to do something. So what would be your idea if you were Larry Page? How would you fix it? So we need to add links to the graph without destroying the initial structure. Because of course you can, if you connect everyone to everyone, then the station distribution would be the same, right? So there would be no rank. So you still want to preserve the initial structure, but somehow to avoid these dead ends, spider traps, and so on. So Google solution or PageRank solution was to make fully connected tiny, tiny links and overlay it on the initial graph. So somehow like this. We have this initial graph that is has disadvantages, but then we make fully connected graph just to make sure that it has a very, very tiny links. And then we overlay it. And now our graph is suddenly conforms, it's fully connected, which weighted, but fully connected. And then because it's weighted, we still have the sort of strong pipes that would give us the rank, but we don't have any issues with the unique convergence. So that's what Google did. And what they said is the following. Let's now, if we think from the random walk perspective, we will say that the random walker with probability beta will follow the real link, but with probability 1 minus beta would jump somewhere, meaning that it uses fully connected tiny, tiny mesh, right? And then our formula will be different now. So before we had basically only this part without beta, meaning that a rank would have been rank of your blue neighbors or blue linked neighbors, weighted by their degree, and we sum up. But now we say, no, we dampen it by beta, plus we collect from everyone their rank. Of course, we get very little because everyone is now fully connected, so they gave us only their rank over n, but we get from everyone, so that's also not so bad. And it's only 1 over beta, and that's our new rank. And usually beta is the sort of following the real links is like 0.8 or 0.9, so it's a majority still here, and this the other part is maybe 0.2, 0.1, meaning that these are very thin links. And then again, from the teleport perspective, and you can think that random walker teleports after 5 or 10 steps on average. So it just walks on this blue graph, and at some point it teleports. Now there's also one caveat is that if you have a dead end, there is nothing here. So then you have to for sure teleport. So then this part should be 1. Okay, so that's, again, make it stochastic. So meaning that if you come to a place where there is nowhere to go to in the real graph, you have to teleport. So again, so what we discussed is this is our random surfer now. Visits a page, throws a biased coin, heads, clicks on a random hyperlink, tails, teleports to a random page. That's the behavior of our PageRank. And then basically now here teleporting was this now essential distinguishing feature of PageRank. And as far as I understand and what I read it, before nobody thought about it. So this is like a unique for Larry Page or his supervisor, his team, I don't know, but basically this was a breakthrough that they figured out, and we'll later see that sort of dealing with teleporting, we can solve many other things. Okay, so then let's see some example. So now we take this graph, we can prepare this our transition matrix, and this graph has an issue with a spider trap here. So you see that this part goes into here, so everything would leak there, and if we would make a original PageRank, you would only get ranks here. Everything for here part would be 0, and these guys would be cycling, so they would be basically equal rank. So very boring, although the graph doesn't seem that boring. So what we say, let's make this now mesh where everyone has incoming link from everyone else. So then we prepare this now a mesh transition matrix, and we can, in the linear algebra point of view, could say this would be the outer product of two vectors of ones, and then we scale it by 1 over n. Okay, so that's our part, and then of course we need to have different weights on each of them, and that's our new matrix PageRank, which would be exactly this, that we take beta of m, 1 minus beta of this matrix, outer product of the column vector of ones, and then dampen it by n. Okay, and then if we say put beta as 0.8, that's how it looks. Of course, you could still identify the fat pipes. They're very similar as here. But now if you find out the eigenvector of this PageRank matrix, now it's more interesting. So it's not anymore as boring as there. And you could see that 3, 4, and 5 are still the best, but now, and even not anymore equal, because maybe some of them are more in periphery, some not in this bigger picture. And then others also got some rank too. So that's what we wanted to have with the PageRank. And that's in a sense the vanilla PageRank, if you like. Now, there are some issues still. So you could see, maybe you can see already what's the issue.
Your number of nodes increase.
In a sense, our edges increased. Nodes are the same, but edges increased. And actually, we have now dense matrix. It's like n squared problem. Before, and think about that, if you these matrices are usually excessively sparse. So if you have millions of web pages, each web page has, I don't know, 10 hyperlinks, 5, or I mean, very little. So most of the matrices these ones are basically zeros, just very little. So it's very easy to calculate, to do the power iteration. While here now we're in trouble. So what again, the practical solution was, that's exactly what we discussed. Instead of this order of n times d, where d is the average degree, the non-zero elements, we have n squared. And if you have, I don't know, billion web pages, billion square, you cannot even store it, let alone process it. It's immense. So what we did is the following. So if you take this our formula, you see, this part we still have to calculate, but this part, if you think about it, if you now take out the constants 1 over beta over n, and you sum up only the Ri, it's 1, because it's a stochastic vector. We know that we have in total 1. So basically, this is just a constant. So we can interpret it as a teleportation tax that is always added to your rank. So what we could do, instead of at this power iteration, instead of calculating this expensive PageRank matrix times the old vector to get a new vector, we instead take an old vector, multiply by a sparse matrix, the original one, dampen it by beta, and just add the tax, where the tax is basically this sum, okay? And then again, if you have the dead ends, then we lose stochasticity, so at every iteration we might need to renormalize. So, but that's technicalities. And then we do it until we feel that the two subsequent vectors are relatively similar. And you can see here's the L1 norm, but any other norm or similarity between the vectors can work fine too. So that's what was the practical, how the PageRank was calculated. It was not calculated with this dense matrix, it was actually did with this tax. Okay. And now this is probably the most famous PageRank example. It's even on Wikipedia. So the bubbles, the size of the bubble represents the rank, right? So the bigger the bubble, the bigger the rank. And now it's pretty interesting example. So you could see that, for example, this guy here, C, no, it has only one in-link and one out-link. So in any other sort of classical interpretation of the goodness, it would be ranked very little. But PageRank, it has very big rank because a very important node points to it unique, sort of exclusively. right? Because this is clearly important, has many incoming links, but it has only one link points into that. So maybe it's some kind of a, I don't know, KTH, and this is the rector. And then, so it immediately sees if your friend is, or whoever points to is important, Nobel Prize winner, immediately your rank goes up. So that's, you know, the one of the feature. Other thing is that nodes that don't have an incoming link still have some rank because of teleportation. Okay, and then other like this and this seems to be similar because they have similar number of degrees, but that one B has much larger rank than E because E is pointed by some very unimportant nodes, right? But B is pointed by more important nodes, therefore it has bigger rank. So that's sort of the interpretation of what we can see when we do the PageRank. So, okay, so the PageRank, this is now we maybe know better what this formula looks like. A new vector would be the old vector times this transition matrix weighted by beta plus some tax. And in this case, if you look at it from the vector perspective, it's just a vector of ones where we add everyone this tax. Okay, so that would be now the first trying to get better acquainted with how to read the PageRank formulas. Or you could look at it from the other perspective, from the linear algebra. This eigenvector is again you construct this PageRank matrix and then see that their eigenvectors are gives you the PageRank vector. But there is more. This is the like if you wanted just vanilla PageRank, now you can leave. Otherwise, if you stay for a bit more, I will tell you what can we do more with that, especially when we now play with the teleportation.
Can I ask a question?
Sure.
About the computation. So you can calculate the fixed points of that without doing the iteration, right?
Yeah.
So, but so is there any reason to iterate practically? Is that numerically better?
It is cheaper. It is the wholly practical, because if you do it, say, with the eigen, you know, finding eigenvectors is usually no cubic performance, while here power iteration is still, because we do it on the sparse matrices, it's much cheaper to do it in the power iteration. And then you don't need to actually find the precise vector, like good enough. So I think in the original paper, when they did with some 300 something million web pages, they showed that after the like 50 iterations, it's good enough rank. So they don't need to multiply for a perfect eigenvector.
A quick question.
Yeah.
So is it the state of art like to use this power iteration to compute the rank vector?
Okay, honestly, I don't really work with the sort of computational part, but as far as I know, power iteration is still used most widely because it's the simplest and the sort of most efficient way to find it for the sparse problems, because these are sparse problems mostly. And you just do the dense part is more for interpretation. Otherwise, we use this taxation that is just adding the extra stuff, not to and you know making the every single vector at every iteration is still stochastic.
Okay. I also have a question that in practice, here n may changes with time. So how to deal with this in practice?
You mean if the
number of web pages?
Okay, so of course this I mean, and you might need to recalculate, but the thing is that if you already have a pretty good rank, so you don't need to start from the beginning, right?
Yeah.
So then you might need to do only a couple of iterations, and then the rank that, say if you add one more node, you can get the rank from the nodes that are nearby, which already converge the rank. So it wouldn't be a big difference anyway. So you don't start from a completely new thing. So it's, but okay, I don't know. And again, this is what Google started with. By no means that's the current state of the art. You know, this was the state of the art in 1998 and maybe a bit later, because people also started gaming PageRank. Then you started having link farms where you would, you know, create a lot of bogus web pages pointing into you and then collecting teleportation sort of tags and funneling into your target page. And then you had to, it's like, mouse and cat and mouse game with always the, you invent something, then there is some, and then you can actually use, you will see later, the personalized PageRank to combat it, But now I don't know what Google uses, to be honest. Probably something completely different with much more advanced techniques, probably deep networks and so on. But this is the classics that maybe everyone should know. Okay, by the way, we are running out of time, so I want you to show more stuff. So again, this thing is maybe now, when you think about it, it's a bit sad that you get only one rank, one size fits all. So if you think, but I would like to know what's your rank in comparison to computer science or to sports or to politics, because KTH is maybe a very good web page for, say, academia or computer science or whatnot, but not very good for sports. So maybe it should be ranked differently. So what they thought is that maybe we can tailor different page ranks, different ranks for different domains. And how can we do that? And here we can start fiddling with the teleportation. So if you remember, initially we say everyone teleports to everyone, or you can teleport anywhere. So it's a fully connected, tiny graph. But what was the proposal is that let's now teleport not to any node, but only to relevant pages for some domain. So say you pre-select only the best sport pages. You say, I will now prepare a new graph with only sport pages, and I will let everyone teleport only there. Nobody else will teleport nowhere. And we can even assign different weights. So basically, we now make a new sort of a, you could say, matrix, where teleportation happens only into some part of the network. And then hopefully the rank of all the nodes will represent how important they are towards this set of pages. And if you have very little rank, maybe that means you are not very important in that domain because you are far away topologically from this set. And again, if you want to see and sometimes it's called personalized PageRank. So if you want to see in practice, so now again, let's take our graph from before, and this is our original matrix. But say, let's make a teleport set 2, 4, and 5. So we say 2, 4, and 5 are now somehow important nodes, maybe some sport authorities. We teleport only to them. So we prepare now a new matrix where you could see now everyone goes to this and nobody goes to 1, 3, or 6. And that would basically be equivalent to taking an outer product of a V, which is a stochastic vector representing where we want to go in this new teleportation situation. And if you multiply by vector of 1, so we get this matrix that we can then dampen by 1 over B. Sum it up, the same business. Eigenvector gives you the rank now of the personalized rank towards this set. And this is sort of a general formula, that one that we see before. So now you can read it, understand how we came it here. And again, now if we see the original page rank without this teleportation would give us for this graph maybe such a ranking, and the highest rank node would be the first. So now after this topic specific on 2, 4, and 5, suddenly the highest node becomes the second one. And maybe not surprisingly, because it got a lot of tags from everyone, while this didn't get any tags. Right, and then the others also relatively their rank increased. And if the graph would be bigger, their neighbors also would have more influence. So basically everyone who topologically would be closer to this set would be more important. And then what I said that you were also combating link farms with this approach, where if you, for example, take only in this set only the very, very how to say, whitelisted nodes. So say, I don't know, Wikipedia and then, BBC and CNN, sort of those that are not really, not spammers. So then everyone could calculate their rank, how to say, close they are to the whitelisted pages. And if you take the ratio between your current rank and this whitelisted rank, you can see how much spam you can have, and then you can identify the spam nodes that would be, having these spam farms, and those would have very little sort of this fraction because they wouldn't be close to the whitelisted nodes. Now, further applications. So there is even one more thing what we can do. We can actually measure the proximity in graph. So like how a specific node is similar to any node in the graph. And that can be very useful in many applications. So for example, in such a graph where we have conferences and authors where they published, if I would ask you, what is the most related conference to ICDM? Just by looking at the graph, that would be not straightforward. You could say, let's take the shortest path, but there are many paths to the other conferences, so we have to have some better measure of proximity. Or what is also very important for recommendation systems, when you have user to product graph, there's a user, this is products, or for Netflix, user and movies, which movies are the most similar, or which users are similar, or which users I should recommend which movies. So the proximity would be very good to figure out. So what they proposed was that if you now take a PageRank with a teleport set of single element, so if you have this V with some only one, then the PageRank, or the station distribution, will give you a proximity distance from that node to the rest of the graph. And the interpretation is that if you now think with this random surfer starts walking from that page, from the one that you set this teleport, walks, but then after some point, it has to return back. It's like PageRank with restarts, right? And what would happen is that if you now, this is the two bubbles connected, you don't see maybe here. So if you now start walking from here, you could see that if you always restart from time to time to this node, it was very unlikely you will reach that part. So to some extent, you localize the regions. So you could see that you are very close to these guys, but really far away from these guys. And then if you say, look at it now, if you teleport to this 5, if you see this PageRank with this teleportation set to 5, you could see the distance is that 5 is actually closer to 2, it has 0.08, than to 7, which is the direct link, which is only 0.06, because it has more paths to 2 than to 7. So in a sense, even doesn't have direct paths, still this measure would have it closer than this one, which is, in a sense, makes sense because these clearly are from a different communities. So basically, we can measure proximity, or we can call relevance or closeness with this tweak that you have a single teleportation point. And from that point, you can then look at the graph and see which is the closest thing to you. And then you can use it for, say, I don't know, Netflix. So say if there's Netflix users, this is a Netflix movies, you could see how close is, say, Alice and Carol. And you can say that if it is from Alice now we teleport, you see that Carol is closer than Bob. And maybe it is true because they share more movies together than with Bob. And similarly, you can see how close is Alice to Star Trek or Harry Potter, and you can see that Alice is closer to Star Trek than to Harry Potter. And it's, again, very useful for link prediction, recommendation systems, clustering, and similar. The problem with this is that you have to do now a lot of job for every node. So when I show it here, this is only from Alice's point of view. If you want a point of view of Star Wars, you need to run again. Basically, you have to run for every single node if you want to. So that's the cost you have to pay. And there are many sort of ways to try to fix it, but that's for another day. And this is called, as we said, either sometimes it's in the literature, random walk with restarts, or rooted PageRank, or there's a SIMRank based on the same issue. So that is that. So now to finish it because now I'm over time. That PageRank and its derivatives were now, since the 20 more years, it was found in many places, like from social networks, road networks, citation networks, biology, chemistry. Were not just some examples, as we saw that at some point Twitter used personalized PageRank to recommend which users to sort of befriend. Pinterest had this Pixie system that also was based on the personalized PageRank. Neuroscience figure out that there is a correlation between the PageRank of a neuron and the relative firing rate. I have no idea, but apparently it is true. And then you can evaluate the importance of brain regions given observed correlations of brain activity with PageRank. Yeah, maybe, I don't know, but seems so. Road network, somebody found out that basically you can predict traffic on some individual roads with the PageRank. And then many others, like in chemistry, like autobibliometrics say now everyone looks at the H index, but somebody wrote a paper, but that PageRank index pi would be much more fair. And then there are some others, like you can identify root causes with monitor with the distributed system with some monitor rank, and there are like zillions of derivatives that you might, Google up and find out, and who knows, maybe even use it for your own research. So with this, I thank you, and I hope you got some inspiration.